37. All right. So it says we have some vertices for a triangle. And we want to find the side lengths and angle measures. So I would start by just kind of like sketching a little bit of a picture. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got 2, 5, 6, 10. And then 5, -2. Okay. So I'm going to start by creating some vectors for each intersection or for each vertex to find the angle. And along the way, I'm also going to end up finding the side lengths. So the first pair is going to be BA and BC. And the second pair would be CA and CB. And that'll actually be enough because I've got all the side lengths covered there with those 4 vectors. And if I get 2 of the angles, I can get the third angle for free at the end. So first thing I'm going to do is turn BA into component form. So head minus tail means 2 minus 6, so that's -4. And then 5 minus 10, so that's -5. And then BC, so again, head minus tail, so 5 minus 6, which is -1. And then -2 minus 10, so that's -12. And we'll do, as long as they're right here, CA and CB. So again, head minus tail, so 2 minus 5 is -3. And then 5 minus a -2 is +7. And then CB, so it's head, so 6 minus 5 is 1. And then 10 minus a -2 is 12. So now that I have these resolved into vector form, I'm going to go ahead and use that angle between 2 vectors formula to find the angle there. So I guess this will be angle B, can write it as. So that's going to be cosine inverse of BA dot BC divided by the magnitude of BA times the magnitude of BC. So cosine inverse, BA dot BC is going to be -4 times -1, so that's 4, plus -5 times -12, so that's 60. And then the magnitude of B is going to be 4 squared plus 5 squared, so that's 41. And then 1 squared times 12 squared is 145. Damn, I spun. So that's 64 over square root 41 times square root 145. So that's 33.90. Now keep in mind that I also found 2 of the side lengths there as well along the way, right? And I'm just going to repeat the same process here for my other piece. So I have here angle B, and I guess this is side AB, and this one is side BC. So again, angle C is the same thing. So -3 times 1 is -3, plus 7 times 12 is 84. 3 squared plus 7 squared is 58. And 1 squared plus 12 squared is still 145. So again, go ahead and do that. Oops. So 81 over square root 58. 58 times square root 145. So that gives me 2796. And I also got side CA here along the way. And so angle A is just going to be that leftovers between those two. So 118.14. I guess. Now it's possible I made some little arithmetic goofo in there, but that seems about right. If I look at angles A and B, those look acute, and angle A looks obtuse in my picture. So I'm guessing I got that right. That seems about right. That feel okay, Tommy? Yeah. So it's just kind of a hassle, there's a lot to do, but it just boiled down to doing, finding the angle between the two vectors formulas. Aiden?
You do number 38.
I mean, it's the exact same process.
You draw the triangle on the...
Yeah, it's almost a straight line.
Okay.
So like the two angles are like decimal points and the other's like 179.
Okay, that's right. I got confused.
So it's like the answer's that's a crazy looking answer, but
I got confused when I did it.
Yeah, the picture is almost a straight line, so the answers are kind of bonkers.
Okay.
So yeah, for sure. But it's the exact same process.
Okay,
Yeah. It probably is one that we should probably just change a couple numbers so it's not quite as bonkers of an answer. Sophia?
Can you do 28, please?
28? Yeah, let's find that. Oh, okay. So 28 wants us to prove that the dot product of u and itself is just the magnitude of u squared. So I'm just going to start by defining my vector u in component form. So u dot u is the same thing as u1 u2 dot u1 u2. So when I apply my formula for dot product, I get u1 times u1, or u1 squared, plus u2 times u2, or u2 squared. Here's the tricky piece. u1 squared plus u2 squared is the same thing as the square root of u1 squared plus u2 squared all squared. And the reason I needed to do that is this is my definition for the magnitude. And I'm done. Right? If I square root something and square it right afterwards, that's the same as doing nothing at all. Particularly when it has to be a positive number, right? If you have two things squared added together, it has to be a positive number anyway, so no worries. Squaring and square rooting still gives you the same thing back. So, you feel good? Who's next? Okie dokie. That's cool with me. So let's jump in here to section 8.3 then. You can always come back and ask more questions later. So in section 8.3, we're going to be talking about applications for vectors. So the first application we're going to talk about is one that we've already done before. And it's something we've already dealt with in first semester. So let's say we have one of these navigation problems. And this should sound pretty familiar, right? A boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 112 degrees and travels 55 knots for 3 hours. What is the distance and bearing of the boat relative to the starting position? So my plan here is I'm going to take the first set of information and convert that into a magnitude and direction, and then take the second set of information and convert that into a magnitude and direction. Take those two vectors as magnitude and directions, convert them into component form, add them together, find the magnitude and direction of the resultant. So the first vector I'm going to call u. The magnitude of u is just going to be 80 nautical miles. And then for a bearing, remember bearings start at due north and go clockwise. So like 215 is over here. But what we're really interested in is this angle here. So if that's 215, that means that little slice was 35. So this slice over here was 55, so that's going to be 235. And I'll call my other vector v. Its magnitude is going to be 165 nautical miles. I'll draw the bearing, so 162 is like here. So that little piece there must have been 18. So there's our direction. So that's going to be 288 then. So that's just me converting the starting information to a magnitude and direction for each vector. I'm then going to convert those two vectors into component form. And then I can add them together to get my resultant vector in component form. So I get 5, 10 for the first component. And negative 222.46 for the second component. Then all I need to do is convert these back into magnitude and direction. Oops. Okay, it's not what I meant to press. So that gives me 222.51 nautical miles. And then if I draw my picture here, if I plot 5.10 and negative 222.46, it's like down here. So if I'm looking for this vector here, theta, this spot between my terminal side and my x-axis is alpha. That side is 360. So theta should be 360 minus alpha, where alpha is the tan inverse of the absolute value of negative 222.46 divided by 510. And I'm going to use the absolute value symbol, I guess, if I'm going to just be stealing these guys. So 271.31. Or if this was, I guess that means that piece has to be 88.69 to get me to 360. And I don't know, I can't remember if we were looking, if it told me I wanted a bearing or a direction. If I wanted a bearing, I guess I would have called this one 78.69 then. But this should all look relatively familiar. It's essentially the same process we were using before. We've just formalized it with vector notations now, right? But it's the same thing that we did in first semester for this kind of a process, so it should feel pretty familiar. Okay. The next piece that we're going to be talking about is new. So let's say we have two vectors. We have this vector v, and then we have this other this other vector, say, we'll call it u. And we want to figure out how much of u is in the same direction as v. So what we're really going to be doing here is looking for this vector here that I've drawn in blue. The name we're going to give this vector is going to be called the projection of u onto v. So what that projection of vector u onto v is basically doing is saying, okay, this much of vector u is in the same direction as v. For the sake of argument, I'm going to name this green vector here that I've drawn in as the vector w. And we would want to make the following observation, that based on the definition of vector addition, this vector u, we have been able to break down into the orthogonal vectors, the projection of u onto v and w. Right? What does orthogonal mean when it comes to vectors? Just that they're at a right angle. So that's kind of our definition. Or, I suppose, with a little bit of rearranging, we could say that vector w then would be u minus the projection of u onto v. So how do we calculate this projection vector? Well, we use the following formula. Oh boy, good thing you have the case. For non-zero vectors, u and v, we say the projection of u onto v is equal to the dot product of u and v divided by the magnitude of v squared times that vector v. So a couple of fine points here about this idea of a projection, and specifically this projection formula. Notice in the original picture that I drew vector v just kind of like arbitrarily large, right? In a lot of sense, the length of vector v doesn't really matter, even though the length of vector v is definitely in our formula for a projection. In a case where the length doesn't really matter in the context of your actual problem, we can choose that vector v to have any length we want. The length we would choose to use in that case would be 1. and just make vector v a unit vector. So the place where we often use this idea of a vector projection in a real world setting is in kind of these, in a lot of physics type problems where you have, like some force happening, but you're really trying to direct it in a different direction. You want to know how much of the force you're generating is actually moving in a given direction, in which case that direction is just, we'd represent with a unit vector with that same direction. We wouldn't need any length to it. Those of you that are in physics classes are often probably did problems that are like, oh, we're pushing a crate up a ramp at this angle, with a force vector going in this direction. Or like, oh yeah, that sounds familiar if you're in a physics class. We've done problems just like that a bunch of times. They can be kind of a pain in the tuchus. The other thing to kind of keep in mind, if we look at this piece of our projection formula, the dot product of u and v is just a scalar, right? That gives us a real number. The magnitude of v squared, just a real number. So essentially what this projection is just a scalar multiplication to vector v. Basically what you're doing is you're scaling vector v, proportionally to this vector u. Okay. So let's do a numeric example here. So it says find the projection of u onto v. Express that vector u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So I'm just going to start with kind of drawing a picture. Now, there's nothing in this problem that really requires you to draw a picture, but for most of us, this is the first time doing this process, and I think that the picture can be quite helpful intuitively to kind of see what's going on. Of course. So I'm going to start by drawing these two vectors. So 3, 1. There's my vector u. And then 6, negative 4. Oops. Here's my vector v. So the green's going to be like my vector w, And my gray here is going to be the projection of u onto v. Is kind of what we're doing. Again, not necessary to draw the picture, but initially, as we're just kind of getting used to this idea of a projection, I'm going to draw the pictures over and over and over again. I think it helps build intuition as to like what's going on and what kind of result would I expect. So I like to keep doing that. Okay. So our example here asks us really to do two things. So it says to find this projection, and then we want to write that vector u as the sum of two orthogonal vectors. So let's do the projection part first. So again, I'll just start by copying my projection formula. Now to do u dot v, I'm going to do the u1 times v1 plus u2 times v2. The magnitude of v is going to be the square root of 36, that's 6 squared, plus 16, that's negative 4 squared, and then times my vector v. So 18 minus 4 is 14. And the squared cancels the square root, so it's just over 52. 14 over 52 reduces to 7 over 26. And then when I do that scalar multiplication, I'm going to reduce the fraction as I go. I get 21 over 13, and then negative 14 over 13. Everybody's okay? I did some fraction arithmetic as I went, just kind of reduced in my head as I multiplied. If you're like, wait a minute, how'd you get the 13s down there? I just reduced the fraction. So that's like the first part of our question, just wanted the projection vector. The second part of our question asked us to rewrite vector u as the sum of two orthogonal vectors. So I can see clearly from my picture that u could be written as the sum of the projection of u onto v plus w. Oops. Here. Wrote that vector w arrow in the wrong direction, my picture. Oopsie daisy. So again, we can rearrange that then by just subtracting the projection of u onto v from both sides. And I now can use that to solve for w. What was that? 21 over 13 and then negative 14 over 13. So 3 is really 39 over 13. So 21 minus 39 is 18 over 13. 1 is really 13 over 13. So 13 minus a negative 14 is 27 over 13. And just as a quick check, if I added these two vectors, 21 over 13 plus 18 over 13 gives me 39 over 13, which is root 3. And negative 14 over 13 plus 27 over 13 gives me 13 over 13, which is just 1. So they do add up and give me u. And I know from the definition of a projection that they are orthogonal because they meet at a right angle. If I really wanted to, I could check their dot product and make sure I get 0. I promise you, you do. That was one of our definitions from yesterday, is that the dot product of two orthogonal vectors is 0. And it works both ways, that if two vectors have a dot product of 0, they're orthogonal. So it's an if and only if statement. So that does that. We feel okay about calculating a projection here. We're going to do some more examples using this, but this was just basically like, can you do the calculation? Which isn't terrible, right? But, you have to make sure that you've got the symbols and the notation down. All right, let's do another example here. This one is more of a story problem, which I know is everybody's favorite. Okay. Here it says Kyle is sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? So again, not totally necessary to start by doing this, but I think for where we're at, it's extremely helpful to kind of draw a picture of what's going on. So I'm going to go ahead and start by doing that. So when I read this question, I hear two vectors. I have the hill vector. So if I draw that, we're going down the hill at 25-degree angle of incline. So I'm going to call that vector H for hill. So the direction of that hill vector is 335. Everybody okay with that? Okay. So that should have been relatively easy. Is there any, are we given any indication as to the length of this hill? No. So what does that mean? We can choose the length of the hill to be anything we want. So we'll choose it to be 1. I'll write choose next to it. Very good. So there's our first vector. We have a magnitude and direction for it. Our second vector, where in the world does it say a second vector? Well, the only other information we're given is that Kyle and the sled weigh 165 pounds, right? So somehow that must be representing our second vector. Physics people in the room, what force is represented by weight? Grace?
Gravity.
Yes, gravity. Yeah, if there's no gravity, there's no weight, right? Okay. Everybody, shh. Again, no gravity, no weight. Remember that mass and weight aren't the exact same thing, right? So, physics people standing on a planet, which way is gravity pulling?
Down.
Down. So our second vector then, here I'm going to call vector G. The direction for vector G is 270 degrees, and the magnitude for vector G is the 165 pounds. So far, so good. I'm now going to resolve vector H into component form. Because we can't do any of our vector projection calculations without doing that. Likewise, I'm going to convert vector G into component form. Oh, 6, 4, 2, 3. Oh, boogers, I don't need to do that. Oops. Notice that for vector G, realistically, to write that in component form, you could have just looked at the picture. You have an arrow pointing straight down with length 165. That better be 0, negative 165. But you could certainly do the calculation I've written down there. And I'm going to write that down every time, even if we can just do it by looking at the picture. Cool? Okay. So now what we want is the projection of G onto H. So let's see, 0.906 times 0. I don't have to worry about that. And then negative 0.42, blah, 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 times, oops, negative 165. That gives me, and then over 1 squared, so 6973. So 6320 and then negative 2947. Oops, 2947. Everybody's good with that? Now notice that what we asked in the question, though, was the amount of force sliding down the hill. So this is the amount of the 165. This is the amount of the 165, or the gravity vector that's going down the hill. So to get the force out of that, really what we want is the magnitude of that vector. From us doing the examples, right? The forces are the lengths. So if we're asking for a force in this kind of a problem, we're asking for the magnitude of a vector. Okay? And we want how much of that gravity vector is going down the hill. So that's a projection. And we'll do some more examples. Yeah, it is. I'm trying to go, if I'm going too fast, tell me to slow down because you need a minute to process, and I'm happy to do that. I know this isn't easy. Okay, well, I don't know that we have an hour right now, but I guarantee you between this class and the next class, there's an hour to process there.
So I usually need time to forget about everything right now. So that it's like, I'm like, no, I could use like a minute.
Okay, let's just take a minute here. Just take a minute, let things,
It's just like,
yeah, sink in, let it sink in for a moment.
I don't get the whole like, the whole you just have to force
Aria.
On test, will you give us like all of like the questions, like adding that, or no, are we expected to
So if you look at the review, it's already, I think the review and the key and everything is already, oh, the review isn't in there yet. When I post the review, that'll be clear what's the equations that are given and what aren't, right? I do that on every test. So the simple stuff like converting between the two vectors or types of vectors, that's a memorized one. I think the projection formula I would give you. I want to point something out to you guys, though. Look at our final answer. Where did we see that number pop up earlier? The dot product of H and V was also the magnitude of the projection of G onto H. Well, what was special about this problem? Yeah, we had a unit vector. So the projection, let's say if the magnitude of V is equal to 1, then the magnitude of the projection of U onto V is equal to the dot product of U and V. Actually, we should probably say the absolute value of the dot product of U and V. because the dot product of u and v could be a negative number, but a magnitude always has to be a positive number. Let's prove this, right? That's what we're seeing. Do we know that this is always true? Let's try to prove this. So I'm just going to go ahead and start by replacing that projection with its formula. Lexi,
Are we gonna have to replicate that?
what do you think? No.
Nice. I really hope not.
If I do, I'm not writing this.
Okay, so all I've done is I've just set this up, right? I replaced the projection with its formula. Notice in the projection formula the magnitude of v. In this case, we know the magnitude of v is equal to 1. So this just becomes everybody's okay there? And now u dot v, the dot product is just a real number. It's a scalar, correct? I can pull that out of my magnitude since it's just a real number. Doing that, though, I have to put an absolute value symbol around it. And then what's the magnitude of v again? Just 1. So this is true. So if we go back to the problem that we were working on a moment ago, since we know h is a unit vector, really we can shortcut all the way down and just kind of stop when we do the dot product. And that's all we need. Now, is it always going to be this way? No, right? I went and did it the long way and made the observation for a reason. Let's do another example. Before we do this next example, do you guys want to just walk through that previous thing again and just re-explain what we did? I'm happy to do that. Okay. So just to rehash, just going to go through this previous problem one more time, explain what we did. So we read the story problem. We identified 2 vectors. We have a vector for the hill and a vector for the gravity. So we drew our hill vector. We obtained a magnitude and direction from that hill vector. Now, since there was no length implied to the hill, we chose the magnitude for the hill to be 1 because it simplifies the problem, but you could have picked any number you want. I don't know why you would pick a different number. And then for our gravity vector, we obtained the magnitude and direction from our picture. We then resolved our vector h and our vector g into component forms. And then we plug them into the projection formula where we're projecting g onto h, the gravity vector onto the hill. So we did h dot g divided by the magnitude of h squared times h to get our component form for our projection vector. And then to find the amount of force that's being directed down the hill, the forces is the lengths of the relative vectors. So we're going to find the length of this projection vector since this is representing the amount of gravity going down the hill. So we use the magnitude formula, and there we're done. Just give a little high-level overview without bogging down in the actual calculation. Let's look at our next example. And this is really going to be the last example for today. I think this is a difficult enough topic that I don't want to try to cram more than one or more than this into one day or this into a day. So here we have a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assuming the crate is of negligible weight, meaning there is no gravity vector involved, what is the amount of force directed on the ramp? So again, I'm going to start by drawing a picture. What are my two vectors going on here? I have a vector for the force on the crate, and then a vector for the ramp. And we're going to be projecting that crate vector onto the ramp to figure out how much of that pulling that we're doing to the crate is actually going up the ramp, basically. Is that okay? So since it says we're being pulled up a ramp, when I draw my crate vector, I'm going to put it in the first quadrant because it's going upward. So it says here that maybe I'll just write this. So my theta C is just going to be 40 degrees. There's nothing to rearrange on that because it's in the first quadrant. And since there's 100 pounds of force, the magnitude for C is just 100. Now my ramp, it says, is 10 feet horizontally and 2 feet vertically. So basically, I'm just going to plot the point 10, 2. And that makes my ramp vector. Oops. Yeah. So there's my picture, right? Now my ramp vector, am I given a magnitude or a direction for this? No, I just told it measures 2 feet horizontally, or 10 feet horizontal and 2 feet vertically. What is it really giving me there? It really just gave me the component form and saved me a step of having to convert it into component form. Does that feel okay to you guys? What should we note here about the ramp, though? Definitely not a unit vector, right? The magnitude of this vector 10, 2 is definitely not 1. Clear as day to see that, right? Okay. I'm going to go ahead and convert C into component form now. So 7660 and 6428. $76. Okay. So now let's calculate the projection of C onto R. So that's C dot R divided by the magnitude of R squared times R. So that's going to be 10 times 7660 plus 2 times 6428 divided by 10 squared plus 2 squared times the vector 10, 2. And I think I'm going to do this all at once. So we have 10 times this times another 10 divided by 104. So 7366. We have 2 times 64 times another 2 divided by 104. So that's not right. What happened here? Something happened here. Hold on one second. I had to type something wrong into my calculator because I'm a dummy somewhere. Okay, so that number's fine. And then with R, so they multiplied that by 10. Okay, divide that by 104. Okay, multiplied that by 10 again. Why is that not coming out to the number on my sheet? Oh my God, okay. Mr. Kulik, you are the king of the dummies. All right. And I don't know why I pressed clear, because that didn't help me any. Okay. Let's do this one more time real quick. Try again. Okay, I promise I haven't written down anything wrong. I've just typed things wrong into my calculator because sometimes let's do this way. 10 times this plus 2 times this divided by 104. Gives me that. Okay. And then that I multiply by 10. 8602. And then I take that same number and multiply it by 2. 1720. That's much better. Mr. Kulik, you were being so dumb before. I'm embarrassed to even have let you guys watch me do that, but I don't know what I was doing. But My family overslept this morning and I've been out of sorts all day. I think the iOS update on my iPhone killed my alarm last night when it did the update. So everybody overslept in my house and it's been kind of a frantic, hectic morning. But we all got here. And there we go, 8772. And we should probably say up the ramp, right? Let's be clear. All right. So at this point, you guys should be able to do 41 through 50 from the problem set. Just a heads up, we should probably be expecting a homework quiz, I don't know, Thursday or then Monday. Kind of one of those days-ish.
Monday.
Hey, look, this is not up for discussion. I'm just trying to give you a heads up of when this thing might be coming. Not looking for input right now, but that's nice that you feel like you want to give it to me. Just to make sure that, like, if you've been putting off doing your homeworks, that maybe you get a jump on that.
Will this be on it?
Not until we go over it in class.
Hopefully it doesn't. Unlistened.
Yeah, okay.